This video is part of an online course of multivariable calculus, and I'm going to talk about integral of vector fields over surfaces. Okay, so let S be an oriented surface in R3. Okay, we talked about oriented surfaces. Actually, it means that there is a unit normal vector n vector at each point on the surface S. Okay, and then let F be a vector field that is defined on S. Be a vector field that is defined on the surface S. Okay, now I'm gonna define the double integral of the vector field F ds over the surface S. Okay, we are gonna say that it's the double integral of F dot n ds over the surface S. Okay, so what is n? N is basically the normal vector to the surface, and since the surface is orientable, the normal vector exists. Actually, it's unit normal vector. Then the vector field F is the vector field, and this little dot in here is the dot product, because I have a vector field in here, I have another vector in here, so that's why I need the dot product between them. And then ds in here would be the element of surface area, element of surface area. And you should notice something, and it's that F here is the vector field, and F dot n here is just because it's a dot product, it's a function. That's why we can use the element of surface area, and we don't need the vector ds in here. The whole thing here is a function. Okay, so now there are some notes. The first one is that the double integral of f dot ds, which we define it like that, is actually flux of the vector field f through S. And by flux, I mean the net flow of a fluid through S. Through S. Basically, the amount of energy of the vector field through S. Okay. The second note is that this double integral of f ds over the surface S depends on orientation on S. Depends on orientation of S. Okay, so if we change the normal vector to the negative n, then the integral would get a negative sign. Okay, so basically we just have a negative sign over there. So the integral of f dot negative n ds over S is basically the negative integral of f dot n ds over the surface S. When we change the negative sign, it is like we have negative s in here and s in here. You see, that's the difference between them. And then the third note is to how to compute that. How to compute? Well, the first thing is to, as usual, we need to parameterize the surface S. Parameterize the surface S. I'm going to use two parameters, u and v, and then I say u and v, they live in a region D, which is a region in R2. Then I need to find the normal vector n. The normal vector would be derivative of r with respect to u cross product with derivative of r with respect to v, and I'm going to divide it by its length to make it unit. It's very important that I need to put the unit normal vector into the formula. And as a note, you need to check that the orientation is correct. Check the orientation is correct. What do I mean? I mean the vector, the S should be positively oriented. It means that the kth component, the third component of n should be positive, and so I get upward orientation, which is positively orientation. Or if S is closed surface, then n should be outward to make it positively oriented. I talked about orientation in previous videos, so make sure that you check that out. And then I'm gonna calculate f dot ds over s by saying that I'm gonna plug in my parameterization into the vector field, and then I have n in here, the normal vector. Let me plug in the normal vector in its place, ru, and then rv, and then ds, the formula for ds we calculated before, which is what? Which is r with respect to u, r with respect to v, du dv over the region D, and I'm gonna cancel out these two. That's why I get a very clean formula for double integral of f dot ds over the surface S, which is what? The double integral of f, put the parameterization into the vector field, and then r with respect to u, r with respect to v, find the cross product of these two, dA over d. This is the formula that we are going to use when we want to calculate the double integral of a vector field over surface S. Now let's look at this example. Find the flux of the vector field F with the coordinates xy for x squared and yz, where S is the surface z equals to x e to the y, x between 0 and 1 and y between 0 and 1 with upward orientation. Okay, so if I want to graph the region S, it's not a familiar graph, so I'm just gonna show it to you, the graph of it, which is x e to the y. That's the graph of it, and we just need to consider it on the square 0 1 0 1 and here. So just this part we want to consider as the flux that goes through this part of S. Okay, so let's look at the formula for the flux. I need to find the double integral of f dot ds over the surface S. Okay, so if I want to use this formula in here, I need to find n, which is the unit normal vector to the surface S. And if you do that, you need to parameterize the surface S and then find the cross product of the partial derivatives over its length, and instead of ds, write this formula. At the end of the day, instead of doing that, I can use this formula and solve it. Okay, so I'm gonna use the double integral of f, r of u and v, and then r with respect to u, r with respect to v, the dot product between these two, and then dA. Okay, so let me parameterize S. So r of u and v, I'm gonna let, actually let me write it like that. I'm gonna let x to be my u, y to be my v, and then z to be u e to the v. U e to the v. And so r of u and v would be u v and then u e to the v. Okay, so now I need to find the cross product of r with respect to u and the partial derivative of r with respect to v. I, j, and k. So what is partial derivative of r with respect to u? It would be 1, 0, e to the v. What is partial derivative of r with respect to v? It would be 0, 1, 0, 1, and then u e to the v. Okay, so let's find this dot product in here, which would be negative e to the v, and then negative, I'm going to remove the first row and the second column, it would be u e to the v, and then the third row it would be 1, and it's perfect, it's just because it's the upward orientation. It means that our surface is actually positively oriented. So I don't need to multiply it by a negative sign. I can just keep it as the way it is because it's positively oriented. So then the double integral of f ds over s would be the double integral of, I'm gonna plug in my parameterization into f. So x would be u, y would be v, and then on here I have 4u squared, and on here I have y, which is v, and then z, which is this coordinate, e to the v. Dot product with this, which is negative v, negative u e to the v, and then 1, and then dA, which could be du dv or dv du. Okay, I'm gonna do du dv, and then u, which is basically my x, is between 0 and 1, so I'm gonna say u is between 0 and 1, and then v is actually in my parameterization is y, and y is also given between 0 and 1, so v between 0 and 1. Okay, let's find this dot product in here. 0, 1, 0, 1. It would be uv negative e to the v minus 4u cubed e to the v plus uv e to the v, and then du dv. These two would be cancelled. Okay, so I have 0 to 1. I'm gonna take this integral with respect to u first. So I have negative u to the power of 4 over 4, which would be, actually let me write the whole thing. So 4 u to the 4 divided by 4, and then e to the v, and then u is from 0 to 1, and then don't forget the outer integral dv. So 0 to 1, these two would be cancelled. Plug in 1, I get a negative 1, minus plug in 0, I get 0. So I get just negative 1, and then I have e to the v dv. So it would be negative e to the v from 0 to 1, plug in 1, negative e, minus plug in 0, which is 1. So I get 1 minus e as the answer for this integral. If the surface was downward orientation, it means that it is not positively oriented, so that's why I needed to multiply my integral to the negative sign. But this one is positively oriented, so I'm fine.